Questions on 13.9? Divergence theorem tends to be okay. It's not one of the harder ones that we've done. Okay, so I guess we'll just pick up where we left off. Remember we're doing linear algebra? Linear algebra 101. Okay, so last time I defined what it is to be a square matrix, I think, right?
You did.
And then we went off on a tangent. Okay, so let's continue with the definitions. Definition 8. One by n matrix is called a row matrix or row vector. Right? So they call it a vector because it sort of looks like a vector. You don't necessarily think of it as something having magnitude and direction as you usually think of vectors, but that's what it's called. So example, that's a row. 1, 0, 1. M by 1 matrix is called, what do you think it's called?
A column matrix?
Column matrix. Or column vector. Okay, so examples of those. 1, 2, 3. Right, so you just do. Okay, so that's that. Talking about now equality of matrices. Two matrices of the same size, of course.
Is that something as a square matrix?
By size, I mean dimension. Are equal if corresponding entries are. So, 1, 2, 3, 4 is equal to 1, 2, 3, 4, obviously, because the first thing in the first row here is 1, the first thing in the first row there is 1. Right? All corresponding entries match up. You say it's equal. And that's obviously not true, because there's a 3 here, there's a 4 here. So that's obvious, but there are going to be times when we're going to want to solve equations with matrices, and that's where knowing about equality comes into play. So for example, if you're given that, simple example here, 1, 2, 3, 4 is equal to 1 x minus 2, 4 minus 1, 4. Then, what would x and y have to be?
1. Y equal to 1.
X has to be what?
0. Oh, sorry, 4.
X would have to be 4, and y would have to be
Y would
what?
have to be, is that minus or times?
Minus.
Oh, 1.
Right, it would have to be 1, because basically corresponding entries have to match up. So you have to know how to match matrices up. Right, so you must have 4 minus y equals 3, which implies this guy. And you must have that 2 is equal to x minus 2, which means that, which gives you that guy. So just know two matrices are equal or corresponding entries are equal, and of course to have a corresponding entry, you have to have the same size, same dimension, same number of rows and columns. That was definition 10. Let's talk about definition 11. Here we're going to do an arithmetic operation, matrix addition. And subtraction. You can add, respectively subtract. It's not really grammatically correct with the subtract word, but whatever. You get the idea. By adding, respectively, subtracting. Corresponding units. Example, that just means that matrix A, B, C, D, and I want to add or subtract E, F, G, H, then this is just the matrix A plus or minus E, B plus or minus F, C plus or minus G, D plus or minus H. Right? So addition is done in the obvious way. You just add or subtract corresponding components.
What if they don't have the same dimension?
Right, I was going to mention that just now. So the mere fact that I mentioned that they have to have corresponding components sort of implies that they have to have the same dimension. In this particular note, the matrices must corresponding entries just mean the entries with the same subscript. So this would have the subscript 1, 1. The matrix here would have the subscript 1, 1. Right? If they don't have the same dimensions, the subscripts won't match up. You won't have corresponding guys. So addition and subtraction are defined only for matrices of the same size. I can
Another example?
do an example with actual numbers. So in the first one, right, just add corresponding entries. So you have a 1 plus a minus 1. Okay, then you have a 2 plus a 7. Then you have a 3 plus a 2. Then you have a 4 plus a 9. Okay? So this would give you 0, 9, 5, 13. Similarly here, you'll have a 1 minus a minus 1. You have a 3 minus 2. You have a 7 minus 3. You have a 9 minus 0. So this gives you 2, 1, 4. Any questions? I guess not. Is it confusing?
No.
Okay.
Not even noticed.
All right. So that's sort of the weird thing with linear algebra. At any given time, you're really doing very simple things. Adding two numbers, multiplying two numbers. Just basic arithmetic. The trouble comes when you have a huge matrix, which we will be doing, 4x4s, 3x3s, and you're going to be doing all sorts of stuff with it. You don't need calculus for this.
Why do we think it's at the end of calculus like?
It's linear algebra. It's the linear algebra part. It's important. We're going to actually use it to do, you're going to see applications later on.
Okay.
We're going to use it to solve systems of equations and differential equations, and there are lots of stuff you can do with matrices. Yeah, so anything you're doing at any given time is really simple. The trick is, sometimes you're doing it so often and there's so many numbers, it gets confusing and you end up making a mistake. But that's basically how it's going to be. You'll see that there's not really anything complicated at any given time, but when you have to do all of it at once, it's sort of you can mess up because of the sheer tediousness of it. Yes. So 12, scalar multiplication. So we multiply the matrix by a scalar by multiplying each entry by that scalar. All right, so scalar multiplication distributes across matrices. So, for example, if I do 2 times 1, 2, 3. So I have a scalar multiplying by a matrix. I can actually do scalar multiplication with matrices. You just simply distribute it across all the components, right? Just like you would a vector. All right, so this is just 2 times 1, 2 times 2.
I feel like we do the same thing in that lab.
2 times 4. So this is just 2, 4, 6, 8.
Yeah, I feel like we just did this in that lab before.
Yeah. Okay, let me define what the zero matrix is.
0, 0, 0, 0.
Yes. 13. You guys laugh, but it's not as obvious as you would think it is. Right? It's obvious because you're doing the basic linear algebra, where we're only doing linear algebras over the rational numbers with usual addition and subtraction. There are other instances where 0 does not look like 0, 0. Right? But here it does.
Question, do you use matrices in probability?
Huh?
Do you use matrices in probability?
Oh yeah, matrices are everywhere. Okay. Everywhere, literally everywhere. Like every single math class I've ever taken at the graduate level, at some point we use linear algebra. Like every one of them. It's everywhere.
Wait, you had graduate probability? You had graduate probability?
No, I didn't take graduate probability.
Okay, that's crazy, I hear.
Yeah, it is. So example, I can write 0 to be, if I want a 2 by 2 0 matrix, I could do that. Or 0 could be a 3 by 3. Right, depending on the context, you'll know what dimension you need to use. Should be obvious, right?
So 0 vector.
Yeah, but 0 is so. If I define addition this way, what's 0?
A plus E must equal 1.
What would the 0 matrix look like with this definition of addition?
4. 0, 0, 0, 0.
No.
Is it 1, 1, 1, 1?
Minus 1, minus 1, minus 1, minus 1. Okay? So I say, let's define the 0 matrix. Oh, well, you don't have to define it. It's not always obvious. It depends on what system you're working with, how you define addition and multiplication. I could define a random operation, and then my 0 would have to be the matrix such that when I add it to any matrix, I get itself. That's what it means. 0 is the additive identity. That's how you define 0.
Wait, is that also because if you have any two matrix, it's also like a triple sum of those two matrices and the zero matrix?
No. I mean,
Because
you can look at it here. If I take 0, 0, 0, 0 plus A, B, C, D, what would I get according to that definition? I would actually get A plus 1, B plus 1, C plus 1, D plus 1.
Where's 1 come from?
It's in my definition. There's a plus 1, plus 1, plus 1, plus 1.
Zero matrix?
Yeah, right here. Right?
What
I
is the
define
one?
addition this way.
Wait. Did you circle that plus, or is that's how you're defining it?
Yeah, I don't want to write the regular plus sign because then I don't want
Oh, so you just.
I'm just defining a new plus. This is a new way. Right? We're in a different universe now where addition is, this is how we add things in this universe.
You just add-
Right? In this universe, what would 0 look like is what I'm saying.
You have to define 0 this
Right?
way.
It cannot look like 0, 0, 0, 0 because if I add it to this matrix, I don't get the original back. 0 should be a number such that when I add it to something, I get the same number. Here I added this guy to this, and I don't get the same guy back.
So in
There's
the-
no way that's 0.
So in this new universe, we add -1.
Right, so in here, if I do this guy though, and I add it to A, B, C, D, according to that definition, I would have A minus 1 plus 1, B minus 1 plus 1, C minus 1 plus 1, D minus 1 plus 1, and that will give me the original matrix back.
What do you care about new universe though? I mean,
Not everything is the real numbers, and we don't always want to add the way you've been taught to add in preschool. Life actually gets more complicated, and sometimes you have to define things in a more complicated way to model certain situations.
probably because, for example, Newtonian kinetic equations isn't actually how nature works, right?
Come here.
Like the Newtonian equations that we learned aren't actually how the universe works. So we have to redefine it.
Well, yeah, so if you want to get into like string theory and all that stuff.
Yeah.
That's beyond our scope here.
Okay.
15, right? But for our purposes, addition is the regular addition you're used to. We're always going to have real numbers here, and we're going to use the regular addition and subtraction, so our 0 should look like this.
Wouldn't it be 14?
Huh? 14. So I'm going to introduce a notation here for the sole purpose of defining matrix multiplication, then we'll probably never use it again. But you will see it in your first homework. Sometimes we represent n by n matrix A by
So isn't it a new matrix?
Alright, so I can think of it as a matrix of vectors, where each vector is a row. So for example, if I look at 1, 2, 3, 4, I could write this as A1, A2, where A1 is just the row vector 1, 2, and A2 is just the row vector 3, 4, right? So I take each row and make it into a vector, and just write it like that. Take this row, make it into a vector, write
Can we
it
have
like
a
that.
vector that represents like both the row and the column at once?
No, that would be confusing in general. Or we can represent as so in other words, for this same example, 1, 2, 3, 4, I can just decide to represent this guy in terms of its columns. Right? I can just call this represented by A1, A2, where A1 is the column matrix 1, 3, and A2 is the column matrix 2, 4. So I just called this guy A1, called that guy A2, and I can represent the matrix that way. Yes?
So A with a parentheses will represent the row and A
Yeah,
without.
if you, the subscript, it's the notation. The subscript with a parentheses just means you're thinking of them as row vectors.
Okay.
If I don't put the parentheses, you think of them as column vectors. So you're going to see that notation in your first homework, I think, and you'll also see when I define multiplication, and then we'll never see it again. Okay, so we're at 15. But A and B be matrices. We say A is conformable with respect to B if the number of columns in A equals the number of rows in B. Right? Right? It's not a relationship that is symmetric, right? So you can have A be conformal with respect to B, but B is not conformal with respect to A. For example, if A is a 3 by 2 matrix and B is a 2 by 5 matrix, right? The number of columns in this matrix equals the number of rows in this matrix, but the number of columns here is not equal to the number of rows there. So in this case, A is conformal with respect to B, but B is not conformal with respect to A. Let's go to matrix multiplication. Suppose A is a m by n matrix,
M by N.
and B is a n by p matrix. Then A is conformable with respect to B, and only then we can define A times B to be the matrix given by AI. Pij, P for product, where
You have P right there. So you're not using it.
Pij is equal to Aij. So let me write it out a little bit.
Is there a difference between it having parentheses in the subscript or not?
This just means I'm thinking of these as the row vector times the column vector. Think of it as a dot product.
Okay, but so the parentheses doesn't matter then.
It doesn't matter. That is write A equals A1, A2, all the way down to AN, N, and B equals, so I represent A as a bunch of row vectors, I represent B as a bunch of column vectors. B N, so the number of columns is P. I have M rows here. And I have then A, B would be equal to, here's how it's going to look. You're going to have A1, B1, A2, B2, A3, B3, A1, holds 1, etc. That.
Oh, so you use parentheses whenever we do rows?
See the pattern? You always have A1 in the first row. You always have A2 in the second row. And then the A's, each row of A populates a new row, right? So the first row of A, that guy gives you the first row of the product. Second row of A will give you the second row of the product. But you take this guy and you go through all the columns of B. you're just taking a dot product, right? So you're taking these dot product. Okay? And that's how it's defined in general. Let me give you a more concrete example. We did this last time. A, B, C, D. So this is your A1, right? You're going to take the first row times the first column. This will be A1 times B1. And your dot product of them. So it's this times this plus this times that. All right, this is going to be your A1, B1. Then you do the first row times the second column. So that's AF plus BH. This is your A1, B2. So once you take the first row of the first matrix and you go through all the columns of the second matrix, and each one of those gives you a different number in the first row. Then you repeat the process with the second row of the first matrix, and then that's going to give you numbers in the second. So then you take CE plus DG and CF plus DH. So this is A2B1, A2B2. So this is the first non-obvious definition that we have, which is what my discussion was about at the end of last class, is why would you define multiplication this way? Precisely, that's what I was explaining. You're thinking of it as functions and you want the input variables to match with the output variables and all that stuff. But basically this is what it's going to be. If you write it down as an algorithm, this is what it would look like. And so, note, AB will be an M by P matrix. So you have your A and your B. This was an M by N. This was an what did I say? N by P. Right? So these two numbers on the inside have to be the same. Must be equal in order to find AB. This is precisely what it means to be conformable. If you write them out in terms of dimensions, the inner numbers have to match up when you put them beside each other. If you look at the outer dimensions, this gives the dimensions of the result. So these guys have the number, whatever numbers these guys are, that's going to be your result. So you have to check that these numbers are the same, and that means you can actually multiply them. The result will be an M by P.
If you try and it's not the same, what happens?
Huh?
If you try and it's not the same, what happens?
You made a mistake, right?
Okay.
So if you know two matrices can multiply, it means you can multiply any two matrices if the number of columns in the first one is equal to the number of rows in the second one.
So it's conformal.
And that means they're conformal, right? Conformal means you can multiply the first guy. If this is conformal with respect to that, then you can find the product of this times that, right? And then the result, your result should be the number of rows in A with the number of columns in B, right? And this is because you're matching up the domain set with the dimensions of the domain set with the dimensions of the range set. Doesn't matter. You can take it just as a definition if you want, but behind the scenes, that's really what's happening. What I was talking about at the end of last class, which you're not going to really need to know. You really need to know the definitions, right? So let's actually do some concrete examples, right? So you guys know what I'm talking about. Say I have this matrix, 1, 2, 3. First, let me make that note first. So know that multiplication is not commutative. We know that conformable is not a symmetric relationship, so therefore you need conformability to multiply. It means that you can't multiply in both directions. That is, AB is not the same as BA in general. Indeed, one can exist and the other might not even exist at all, right? They can be that different. Right, one could be undefined.
If it's a square matrix,
Right.
then only do the same.
If they're square matrices of the same size, then it's you can actually multiply both sides, but it's still not guaranteed that they'll give you the
Same answer?
actual same answer. Right? So, example, if A is I did an example before, a 3 by 2, and B is a 2 by 5, then we can find a B, but BA doesn't even exist. Right? They're not the same in general, right? So the order of multiplication in matrices matters. This is one of the first real big differences between just ordinary real numbers and matrices. Addition and multiplication, they're sort of obvious and they do commute just as every day, but multiplication here is actually the composition of functions. So it's actually the properties of multiplication vary from what you're used to. Right? So you should note that. Multiplication is not commutative for matrices. AB is not the same as BA in general. One can exist and one can even not exist. It's that big of a difference. They're completely different. In general, think of them as different things. So now let's do an example. Let's say I want to find 1, 2, 3, 0, and I want to multiply that by the matrix 1, 1, 0, 1, 1, 2. Is this a well-defined multiplication?
Yes, it is. Yes, it is.
Right? This is a what? What size here?
Cumulative.
Huh?
2 by 3.
So 2 by 3. This guy is a
3 by 2.
3 by 2, right? The inside numbers match up. You can multiply.
So it'll be 2 by 2.
Right. What should be the result size? Right? The result should be a 2 by 2 matrix. Right? So you do this check to make sure you can multiply them. The outside numbers are going to tell you what the size of your answer should be. So if you multiply these and you get another matrix that's not a 2 by 2, you made a big mistake. Right? So let's actually do it. So, how do you do it? So remember, the first row of your result is populated by the first row of the first matrix. So I'm going to take the first row here, run through all the columns, and that's going to give me the first row of the result, right? So take this row here. First row times first column is going to give me the first number. So that's going to be, and you think of it as like a dot product, right? This times this plus this times that plus this times that. 1 times 1 plus 2 times 0 plus 3 times 1, right? So this is the first row, first column, right? First row, first column, right? Notice that this gives the A11 term, right? Now if I take the first row times second column is going to be the next guy. That's going to give me the A12 element, right? So now I take the first row times the second column. So it's going to be 1 times 1 plus 2 times 1 plus 3 times 2. And then we stop. We ran out of columns, so we have to move to another row now. So now I'm going to repeat the same in the second row. So I'm going to take the second row times the first column, right? That's going to give me the A2 one, right? The 2 and 1, A2 1 term, right? So then I take this times that. That's going to be 3 times 1 plus 4 times 0 plus 0 times 1. Okay, the second row times the second column is going to give me over here. That's going to be 3 times 1 plus 4 times 1 plus 0 times 2. This is the second row times the second column. This gives me the A2 2 term. Right? So the product of this matrix actually looks like 1 plus 3, that's 4. 1 plus 2 plus 6, right? That's 9.
Oh, the only thing about, yeah. No, sorry.
What?
No.
What do you say? Yeah, this is what I'm talking about. It's simple operations, but when you're doing a lot of them at the same time, you get confused. Right? This is 3 plus 0, that's just 3. And this is 3 plus 4 is 7 plus 0. Right? And this is a 2 by 2 matrix. So I know we did it correctly.
So you're always ending with a square matrix?
No, you don't always end up with a square matrix. You end up with a matrix that has this dimension by that dimension. If this was a different dimension, which it could be, I could put a 5 here, and the result would be a 2 by 5.
Okay, so can we test it out with B times A to see if it's different?
You got a 9 by 9 matrix.
So let's actually see if, can we actually multiply B times A?
Yeah, we can.
Yes.
Yes, we can.
We'll have to divide the matrix.
Let's switch. What if I looked at it as 1, 1, 0, 1, 1, 2 times 1, 2, 3, 3, 4, 0. Then I look at the dimensions here. This is a 3 by 2. This guy's a 2 by 3. So yeah, these guys match up. We can multiply. The result is a 3 by 3. Right? So when I actually do this multiplication, I should end up with a 3 by 3 matrix. So here's an example where both directions can multiply. AB exists and BA exists. Let's see if they're the same.
They can be the same. It's completely. Come on.
Why would you say that? You don't know.
It's.
So yeah, let's do this. Okay, so you take the first row times the first column, that gives you the first number in the first row. 1 times 1 plus 1 times 3. Take the first row times the second column, that gives you the second number in the first row. 1 times 2 plus 1 times 4. Take the first row times the third column, that gives you the third number in the first row. 1 times 3 plus 1 times 0. Right? Repeat the process with the second row. Take the second row times the first column, that gives you the first number in the second row. Second number times the second column, second row times the second column gives you the second number in this row. So it's 0 times 2 plus 1 times 0. Second row times third column, 0 times 3 plus 1 times 0. Repeat with the last row. This row times that column, 1 times 1 plus 2 times 3. This row times the second column, 1 times 2 plus 2 times 4. Last row times the last column, we have 1 times 3 plus 2 times 0. So this is going to give you 4, 6, 3, 2.
I think that's 3, not 2. That's 0 times 1 plus 1 times 3.
Oh, this? Yeah. See what I mean? This would be a 4, right? I still
It's 3. Should be 1 times 3, not 2.
So it's
1 times. Where
The
are you
second
talking?
row. The
Your second
row
matrix,
plus
look at the
1.
matrices.
Oh, that's right.
it should be 3.
It's 1, 3, 2. No, Professor, look at the matrix, your original problems. Yeah,
This
that
one?
It's a 3.
This 3?
Yeah.
2, 1.
0 times 1.
Or
and then
which?
1 times
Oh,
3.
here.
It's 3.
Okay. Yeah. Yeah, well, I did the right thing. I just wrote it down wrong the first one. Okay, so 3, 4. This would just be 0. This would be 6 plus 1, that's 7. 8 plus 2, that's 10. And 0. So they're definitely not the same because they even have different dimensions. So obviously they're not equal. You have to have the same dimensions to be equal. Right? So here you see that this guy, if I call this A and call this B, then AB would look like that, and BA would look like that. Right? So AB and BA, they're not the same. Right? They don't have the same dimensions. So there should be a lot more examples of multiplication in your homework, so let's move on. Take some practice to get used to it. It shouldn't be bad after you practice over it. Okay, what definition was that? Because I changed the number in here. What was the last one?
16.
Okay, so let's move to 17. A square matrix.
Okay.
Whose non-diagonal entries are all 0 is called a diagonal matrix.
Why is that useful?
The identity matrix is a diagonal matrix. Yeah, that's one. That's one very useful matrix. Diagonal here refers to the we're talking about the diagonal from top left to bottom right. Example 1002. 100030000.
So that's the right-handed people, basically?
Are diagonal matrices. Right. So once the main diagonal is the guy from the top left to bottom right. Right? So if you find that guy, notice that everywhere else you have zeros, you say you have a diagonal matrix. The zero matrix is also a diagonal matrix because it has zeros everywhere. Diagonal matrices are nice. Not only is the identity, which is an important matrix, a diagonal matrix, but usually with diagonal matrix, it's a lot easier to perform a lot of computations. For example, it's going to be very easy to find determinants. It's going to be easy to multiply two diagonal matrices. A lot of things would work out nicer with diagonal matrices. So a lot of linear algebra is to figure out ways to transform matrices that are not diagonal into equivalent matrices that are diagonal. You can do all sorts of operations with these guys over here and then just transform the answer back. So that's where they really come in handy. A lot of operations become a lot easier with these matrices.
This works on any matrix, so if I have like a 56 matrix, if it's diagonal, I can do the same thing.
If what?
If I have like a 56 matrix.
A 56?
As long as it's diagonal, I can do the same thing.
If what is that? I don't know.
The matrix is diagonal.
Isn't that like row reduced or something? Like you have zeros above.
In this is a diagonal matrix is a matrix in what we call reduced row echelon form. But you can't have non-diagonal matrices in reduced row echelon form also. I could put another row with non-zero numbers here, and I'd still be in yeah. Right. So we'll get to that later on, but this is a separate concept, actually.
Are those square matrices?
Yeah, these happen to be square matrices. Yes, they are square. I only define them as square matrices.
Can you get a diagonal matrix that is not square?
No, it's a square matrix.
So if it's all zeros, then it's considered a square.
It's also
It's
diagonal,
also
right? Because if you look at the zero, like
What if it's a rectangle matrix?
right? Here's the main diagonal. Everywhere else you have zeros. It's still a diagonal.
As long as everywhere else has
yeah,
zero.
as long as everywhere besides the diagonal. It doesn't matter if you have zeros on the diagonal. In this example, I put
Yeah,
one there.
that's what
It doesn't matter what's on the diagonal. As long as everywhere else there's zero,
Okay.
I call it a diagonal matrix. 18. A super important diagonal matrix is the identity. Is the identity. You think of it here as a multiplicative identity, right? So the zero matrix was the additive identity. This guy, we're talking about the multiplicative. Identity matrix. Right? You usually leave out the word multiplicative, right? If someone says the identity matrix, this is the matrix they're talking about. If they mean the additive identity, they'll call it the zero matrix. This is a diagonal matrix with all diagonal entries equal to 1. A is an n by n such matrix. We call it IN. Or simply I, if the dimension
By n?
is known.
N by n?
N by n, yes. So we're going to write down some examples of an identity matrix. Right, so I2, for example, is the 2 by 2 identity matrix. Right? So this is just 1, 0, 0, 1. Right? I3 would be the 3 by 3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0. Right? All along my main diagonal, they're just ones, zeros everywhere else. Such a matrix I call the identity matrix. And as its name suggests, the title, multiplicative identity, this is the matrix where if I multiply it with any other matrix, I get the matrix itself. It's sort of like the one of the matrices. Right? This guy functions as the one. The same properties that one has as a real number, in the matrix universe, this matrix has that property. Right? If you multiply any matrix by this guy, you just get itself. Provided it's conformable, of course.
Oh, so it's like if you add zero matrix to
Right. So the zero matrix is a matrix where you add it to any guy, you get the guy themselves. This guy, if you multiply by any guy, you get the guy itself.
So non-square matrices don't have inverses.
No. Correct.
But,
Correct. Because remember, for inverse, you'd have to be able to reverse the function.
but you
The
would
domain and the
still
range have
have
to be
square though,
conformal.
but you would still have like a square of matrix formed by two non-square matrices by multiplying them. Like we showed with those, the one we were doing before.
Indeed.
In that case, is there?
There is no inverse for either of those matrices, which is sort of the weird thing, right? Another thing with matrices is that that is different from real numbers is that there's no real division. Division doesn't really exist, right? So just because I know this matrix times that matrix gives me a result, it doesn't mean I can divide this matrix by one of those to get the other one. You can't always divide. You can only divide, quote unquote, if your matrix has an inverse. It will only have an inverse if it's a square matrix. Right? So these are some differences between, but we'll get to all that. I'll emphasize all of that when the time comes. Right, so there are a lot of things that are very different with these guys, but I mean, the operations are simple at any given step.
A square matrix or an identity matrix? We can divide if it's a square matrix or if it's an identity matrix. We can divide if it's a square matrix or if it's an identity matrix.
No, you don't think of it as division.
I know it.
Right. You can think of it as multiplying both sides by the inverse.
Isn't it also called
That's how you would think of
Isn't
it.
it also called a chronic or delta, that matrix?
I've never heard that. I don't know.
Okay,
Maybe there is some
all identity matrices have an inverse?
Hmm?
So all identity matrices have
Every identity matrix has an inverse. In fact, it's itself. Yeah. Identity matrices are their own inverses.
Nice.
And you know that In times A is equal to A itself. Or A times In is equal to A itself. It's sort of like 1. Like 1 times anything is the thing itself. Or the thing times 1 is the thing itself. Once they conformal. So once the multiplication actually makes sense, you'll always get the guy itself. Let's continue.
And the A and the IN has to be the same dimension, right?
They don't have to be the same dimension. They have to be conformal. Which means the number of columns here, which is n, should be the number of rows here.
Okay.
But if it's an identity matrix, then the identity matrix must be square.
Yes, an identity matrix is a diagonal matrix. All diagonal matrices are square matrices. Okay. A, if I write A with a uppercase T at the top, the symbol AT is called the transpose of A.
Transpose.
Or in spoken language, they'll say A transpose. Right? So if I say A transpose, I mean this guy. Right? This is the matrix obtained by interchanging the rows and columns A.
So perfect.
Right, so first row becomes first column, second row becomes second column, etc. Let's give you an example. So our trivial example again. If A is equal to this, then A transpose is equal to what?
1, 3, 2, 4.
1, 3, 4.
Right. So my first row is now my first column. My second row is now my second column. Right? Whenever you do this guy, you say you've taken the transpose of A. Right?
As if you're doing
And
this.
note A need not be squared to find its transpose. Alright, so to be a diagonal matrix, you have to be a square matrix. To be an identity matrix, you have to be a square matrix. But to find a transpose, you don't have to be square. You just switch all the rows and columns.
Why is this useful? for engineers?
This guy can help you define the inverse if it exists.
Oh, really? Nice.
Yeah. Yeah, something like that. Example, A could be 1, 2, 3, 1, then A transpose. Or they transpose me.
1, 0, 4, 2, 3, 1.
Huh?
1, 0, 4 along that road and then 2, 3, 1.
Yeah. First row comes first column, second row comes second column, third row comes third. Another thing in this chapter is we're almost done with the definitions. I mean, the last one will probably run into next class, but I can give you the properties. So this is basically going to tell you some of the properties that should be familiar with you. For example, A plus B is equal, like, for instance, at A, B, C, D matrices. Follow and hold. With our definition of multiplication and addition on matrices, all these properties are true. Addition is actually commutative, so that one you don't really have to worry about. Right? It's not true for multiplication. Right? So that's why I have to say these things that it seems obvious to you, but really they're not obvious. There are things that are obvious that just don't work with matrices. So I have to actually tell you what are the obvious things that work. There exists such a thing as 0 with matrices.
Question, is there something that if you multiply by 0, you get 0?
Huh?
If you multiply by the 0 vector, do you get 0?
If you multiply by the 0 matrix, you do get 0.
Okay.
Yes. You can mention that 0 times A equals A times 0 equals 0. This, once they're conformable. Of course, every time in multiplication, you have to think, are they conformable? Is the number of columns and number of rows the same? Right? Multiplication is not just a walk in the park anymore. You have to always be vigilant.
And 0 vectors that don't have
0 is just the guy with all zeros.
So it doesn't have to be a square at all.
Huh?
So it doesn't have to be a square, it can be a rectangle.
No, it doesn't have to be a square.
Okay.
The identity matrix has to be a square, but not the 0 matrix. And amazingly enough, A minus A is actually 0.
Wow.
So, well, it follows from this equation. You can actually subtract A from both sides. In times A equals A times IN equals A. Right? N you would know from context. There is a distributive property.
A is matrix or vector? I mean, or scalar?
ABCs are matrices.
Oh,
Okay? Order matters. Anytime you think of multiplication, order matters, right? If the A is on the left when you're distributing, it has to be on the left in your results, right? You can't put a BA here. It's not the same thing. Order matters when you're multiplying. You can distribute if the A is on the right also. That would give you BA plus. Order matters.
What if you try to multiply two additional matrices?
Huh?
What if you try to multiply two additional matrices? Like AB times B plus string A plus B times C plus D.
Oh, you just applied the distributive property twice.
Okay.
Yeah.
So all of
But the order will matter. Whoever's on the left stays on the left. Right?
Okay,
So
so-
you be very rigid about that.
So all of these properties will be considered obvious?
Huh?
All of these properties will be considered obvious?
Sure, yeah. Yeah. Meaning if you use one of these, you don't have to tell me that you're using it. I know when you're using it. But this one is not so obvious because you might be tempted to write this in any order. The order actually matters. Right? So you have to make sure things line up. Addition is associative. Which means you can move brackets. So if I have A plus B plus C, it's the same as A plus B plus C. And if I multiplication, it's not commutative, but it is associative. That means if I have A times B, and then I take that matrix times C, it's the same as taking A times the matrix BC. Right? So you can't switch them around, but you can move brackets. You can choose which pair you want to multiply first. I'm going to introduce alpha as is a scalar number, right? Which you just think of it as a real number. Alpha times AB is the same as alpha times A times B, or you can think of it as A times alpha times B. So you can choose which matrix you want to multiply the scalar by first. If you take the transpose of a product, the transpose does distribute, but you actually have to reverse the order of these guys. All right, so look out for that one. There's one more thing they do in chapter 1, but I think it's better if it leads into chapter 2, so I don't want to start it and not do chapter 2. So we'll stop this. This is what my professor calls the so-called shoes and socks law. You can't do it in the same order. You put on your socks then your shoes, but when you're taking them off, you have to take off your shoes before the socks. He says that's how he remembers it. I don't know. Whatever, you know, to each his own.
The homework for this is in next class?
Yeah.
Yeah, you should be able to.
Can you explain that one more time?
This?
That.
This is just a number.
Oh, that's just a number?
So yeah, it's just a scale. So it can be
Scalar number.